Welcome everyone to the second RENA presentation. I'd just like to start acknowledging, as a reflection of the institution's recognition of the deep history and culture of this island, the University of Tasmania, Australian Maritime College and RENA wishes to acknowledge the traditional owners, the Palawa people of the land upon which this campus was built, and pay respects to elders past, present and emerging. Tonight we've got a presentation from Daniel Webster, and for those of you who don't know Daniel, Daniel has done a TAFE course in electrical engineering, a Bachelor of Engineering, Electronic Engineering from Victoria University, is currently doing a Master of Maritime Engineering with us at the Australian Maritime College. But most importantly of all, Daniel has been a leading marine engineer, electrical engineer for Tenix Defence Maritime for about 11 years, I think, Daniel. Also with UGL Rail and BAE Systems. He then worked for Seaspan in Canada for a number of years before returning to Australia and working with Serco on the ASRV Icebreaker Electrical Engineering Manager. And we're very fortunate to have Daniel with us tonight. Afraid he couldn't make it to the campus tonight. He's actually in Hobart. He did have a small sniffle last night, and in these days, this time and present events, didn't feel like he should be traveling. And so we're very, very fortunate and very grateful that he was able to actually join in from Hobart, from his home in Hobart, where he's based, and from where he actually went on the RSV Nuyina extensively for trials over the last Christmas period in Europe, and is going to talk to us today about the RSV Nuyina and some of the trials that he did actually perform on that vessel. So without any further ado, Daniel, I'd like to take
Thanks,
away. Jonathan.
Thanks for the introduction. Yeah, like Jonathan said, I'd like to apologise for not being there in person tonight, but I do want to take the risk. Let's start the presentation. As Jonathan's already explained, a bit of a brief of my history. I probably won't go into too much detail. Been working in the industry for 20 years. Currently doing my Masters, as Jonathan just said. And I started working on the ASRV project in 2018 and moved from Seaspan, from Canada through to Hobart to take on that role as the Electrical Engineering Manager. Just before I move on, I'd like just to thank the following contributors to the presentation tonight: the AED, Damen, Serco, and Knut Hansen. For the presentation tonight, I'll just go through a couple of, present a more of a broad picture of the project, the vessel's capabilities and its operations, the propulsion system, some of the production photos and the launch, the test program, as Jonathan discussed before, the delivery voyage, and just a summary. The story of RSV Nuyina. Nuyina is pronounced Nuyina, is a word in the Palawi language of Tasmanian Aboriginals for the Southern Lights. The name Nuyina is reminiscent of the names of previous ships involved in Australian Antarctic research. The Aurora Australis, which has just finished last year, and the SY Arena. Just going into the background of the project, Serco was contracted in 2016 by the Australian Antarctic Division to undertake design, build, operate and maintenance contract of the new Antarctic Supply and Research Vessel, ASRV Nuyina, to replace the existing Aurora Australis. The new vessel has been designed and built by Damen Shelter in naval shipyards under Serco Defence supervision. This is in Vlissingen and in Galati in Romania. Currently, the vessel is going through special sea trials and will be fully commissioned and available in Hobart later in this year. Following the final acceptance, which is in Vlissingen in the Netherlands, the Nuyina will be operated and maintained by Serco Defence out of its home port of Hobart. The RSV Nuyina can accommodate 32 crew, up to 116 special personnel and 1 doctor. It has the ability to embark up to 4 helicopters and 2 landing crafts, which we'll show you in a minute. The vessel's capability platform, the length's 160 metres, the beam's 25.6, draft when fully loaded is 9.3 metres, displacement's 25,000 tonnes. The installed total power is 30 megawatt, the propulsion power is 26 megawatt, the polar class is PC3, speed is 12 knots under electrical and 16 max under propulsion. It's a range of 16,000 nautical miles. Can have endurance of 90 days. Seakeeping requirements come from DEFDOS 5000. And it can break ice up to 1.65 metres at 3 knots. It has dynamic positioning capability up to sea state 4. And that's silent R accreditation, but not notation. Just move on to the next slide. Just a bit more of the vessel capability platform. Class notation, I'm going to go through all of it there. Like I said, ice class 3, winterization -30 degrees, and DP2 PSMR. As we said before, propulsion system. Propulsion system is a diesel electric plus a power takeoff. There's 2 main propulsion engines. They're each 9.6 megawatt, which the propulsion power is 26.6 kilowatts, or should have been megawatt, including the power takeoff and power take in. It's got 2 propellers with CCP, 6 thrusters, 3 forward, 3 aft, all 1.3 meg each. On the electrical side, there's 4 DGs, 3 of them are 3 megawatt and 1 is 2 megawatt. And there's an emergency DG set, which is 1.2 meg. Just a comparison here between the existing Aurora and the Nuyina and its capability. Just like to highlight a couple of key factors here. The increase in cargo capacity from 800 tons to 1,200 tons. The increase in containers that it can handle from 34 containers to 96 containers. And then the liquid cargo, which is Antarctic Special Blend Diesel, from 1.1 million litres to 1.9 million litres. And just to highlight, the number of AAD special personnel is the same, 160 expeditioners. This slide has a lot of information all at once. Just wanted to highlight a couple of things like I discussed before, was the silent R rating, but not the notation. And the reason behind that is that the vessel's built to Lloyd's class, but silent R notation is actually a DNV notation. So we've done the test to the silent R, but it won't get the notation. The operating temperature rating is to -30 to 45 degrees. You'll see there's science tenders, personnel tenders on board, 2 helo decks. And I'll move to the next slide, which probably is a bit more detailed than you can see. Okay, polar code. As I said before, the ship is rated to PC3. What does PC3 mean? PC3 is a year-round operation in second-year ice, which may include multi-year ice inclusions. So the vessel's been deemed to do that, which is rated as Polar Class A. I'll leave the slide for a second just so you can have a read, but I'm not going to go into too much detail in that. Just following on with the Polar Code, it's enforced in January 2017. It's applicable to the design, the construction, training, operations, and rescue. In the analysis for this vessel, the time to rescue means 30 days from support vessel in the Antarctic region, 60 days for a vessel that's in the southern hemisphere, and 90 days support from a vessel in the northern hemisphere. So what's on board? We have group survival kits, GSK, personal survival kits, which involve emergency rations, fuel for making water, and of course tents and to keep you warm and the rest if you're stranded. Also in the assumption of this calculation is that the RAF will support with airdrops that would occur in a 30-day period as well. Just moving into the operation phase, as explained before, it's a DBOM contract. So design, build, operate, maintain, which is a very different contract than most. The design and build, Serco's subbed out the Damen for that. And then Serco has the operate and maintain contract as well. So that's for the first 10 years with 5-year extensions out to 30 years. Okay, the vessel planned to arrive near the end of the year. The operation capabilities in the contract is 200 days a minimum per year for resupply and science, with the potential of an increase of 100 days for emergency response and other government work. So it could be up to 300 days a year, but typically 200 days a year. Some of that emergency response and government work could be for the CSIRO, Defence, Geoscience and Customs. Now, the picture there shows you all the stations that AAD go to. These days they're not going to Heard Island, so they normally go to Davis, Casey, Mawson and Macquarie Island. And then there might be a supplement one, which is for some marine science trials. Especially with the new capability that Nuyina brings, there'll be definitely more science trials being done, but also they could do science trials on the way down to those locations. So just to give you a bit of context of duration of the voyages, V1, which is Davis, is approximately 5 weeks long, and it starts at the end of October to about the end of November. Davis Resupply is about the same duration, 5 weeks, starting from the middle of December to the middle of January. And this is a typical season I'm talking about here. Casey, V3, is from mid-January to the start of March. It's 6 weeks long. And Mawson, no, I've read it twice. Yeah. Macquarie Island, sorry, is the 10th of March to 27th of March. It's about 3 weeks long. With the increase of Nuyina might be able to do 2 station resupplies where the Aurora wasn't able to. The voyage length roughly to go down to Mawson is roughly 10 to 14 days and return is 10 to 14 days. The operating profile for the vessel is really station resupply, which is the expeditioners who go down to Antarctica for the winter. So the 116 expeditioners, the cargo, which is required down there for food, equipment, and stuff like that. And then the fuel down there. I think Mawson takes 1 million litres. Just going into station resupply in a bit more detail. Has the Nuyina has 2 forward cranes, 55s. Has an 15-ton crane. As we said, we talked about solid cargo of 1,200 tons before, and the amount of containers and the liquid cargo. Can have 200 tons of fresh water it can supply to the bases as well. The flight deck is 760 square metres forward and aft, and the aft is got a heated deck. The hangar's got 330 metres squared and is heated. The hangar can handle either 4 light helicopters or 2 medium helicopters. On forward, near the cranes, we can mount 2 45-tonne landing barges, which can carry plant and equipment or a 40-foot container. 3 personnel tenders for transferring expeditioners on and off the vessel. 1 science tender to do science tests. And then at Macquarie Island, we can also put on some larks on the forward to move cargo as well. So just going through some of the pictures for resupply here. The left one is one of the barges, which can handle the 40-foot container or plant equipment. The middle photo, which is the small one with the helicopter, is at Mawson. That's showing you how they actually refuel there. That's actually a fuel line with the rib going around the fuel line to make sure there's nothing going around it. The top right photo is the helicopter during sea trials last year, or in the last year. And the bottom right photo is showing the barge operations that was literally 3 days ago with the vessel. Still following on with some photos from resupply. The top left photo is one of the larks, which is used at Macquarie Island, as explained. Top right-hand photo is one of the science tenders, the only science tender, we get it right. Bottom left, the bottom 2 photos are the barges. There's 2 barges on board. They are built by Taylor Brothers, let me get it correct, in Tasmania. Okay. That was a good trick. Sorry. Look at the wrist. Okay, just moving on to now ice breaking capability of the vessel. So the Nuyina has a knife edge, which you can see there in the middle picture, which has 70mm thick plate, and it's bent and folded down to the center to create a sharp edge. It is supported by 600mm frames with spacing of 25mm frame plates. The area underneath is the ice contact area where large pieces of ice will hit, and it has a 100mm stem plate down the middle. The vessel can also mill ice astern through the props as well. Okay. Just going to explain a little bit of the science operations, but I'm not a science expert. I sit on the electrical side, looking after the equipment and integration of the equipment. But I'll give you a bit of a high level understanding of what's on board. So just looking at this picture, the top part is there's a bomb radar on the top for weather. There's a number of weather sensors on the Monkey Island for the bomb, and there's a bomb compartment for them. There's a marine, mammal, and seabird observation stations. The forward mast there is an air sampling scientific air mast. We also can sample the water forward. Just going underneath now, we have science sensors and acoustics set. We can deploy remote vehicles and recoveries. We can do seabed sampling, water column sampling, and then we can do some fishing stuff like biological sampling and deploying mooring. Just moving into a bit more detail here, talking about the science equipment, because this ship is really a floating laboratory in some way. So there's 500 square metres of science lab and offices, 24 modular science containers that can be used. Aft, there's an 8-metre A-frame, and there's also a modular deep sea coring system. There's some towering booms and winches, trolling system. There's 2 drop keels. There's a CTD system, which we'll explain in a second, with the moon pool. And there's a wet well for scientific sampling underneath the ice. And I just explain the bomb equipment and chemistry labs. And there's also a forward deployment boom to go onto the ice. In the pictures here, you'll see on the bottom right, the sort of layout for the laboratories. You've got 2 wet labs, 2 dry labs, plus a science freezer, and some cold stores. And in the top right is the photo of the wet lab. Just going into the sensor suite stuff, we have a lot of science sensors either on the hull or in one of the drop keels. So we have a deep water wideband echo sounder, a high resolution multi-beam echo sounder, and we have 2 of those, one on the drop keel, one on the hull. Same with the sub-bottom profiler. We have 2 different frequency acoustic Doppler current profilers. We have hydrophones, different frequency hydrophones on the hull and in the drop keel. We have a side-looking fisheries sonar in the drop keel. We talked about the bomb sensors. We have an ultra short baseline, and I'll explain that in a minute. And then we have, it has the capability to use an XPT probe system where they drop it over the side and measure the temperature, and then the CTD. So just to go through some of these photos, there's a picture there of the Antarctic crew on the bottom left-hand side. I'm not sure if you know much about the science of what AAD do, but they spend a lot of time studying the krill. And the reason is, it's one of the keystone species of the Southern Ocean, and it interlinks the whole ecosystem together. So by understanding those effects, they can understand the ecosystem down there. The AAD in their office actually have a krill growing facility and tanks. So they'll catch krill and they'll bring them back. The other photos there is actually the CTD room. The top right-hand side, you'll see the CTD crane, the CTD deployment wind door, and the CTD itself, which is there. The CTD, which is a bunch of bottles, is lowered down either through out the hatch or down through the wet well, as you can see on the bottom right. And at certain temperatures, certain depths, the bottles can be closed to capture the water, and measures the salinity, the density, and the temperature at that point. Just stepping through the drop keels that we talked about before. There's 2 drop keels, as I explained. One is populated with sensors and transducers. The other one is not. The left-hand photo shows you the positions that the drop keel can be in, from fully retracted to maintenance position to semi-deployed to fully deployed. So it has 3 intermediate positions, a navigation position which is flush with the hull, 1 extended position at 3 meters, and then a maintenance position and a stored position. Just to explain a little bit more around the ultra short baseline. The ultra short baseline is a method of underwater acoustic positioning. A complete USBL system consists of a transceiver, which is mounted on a pole under the ship, a transponder or responder on the seafloor. So the transponder is the yellow item in the middle. That's dropped on the seabed, or the red item on the left picture. The HIPAP, which is the hydraulics for the USBL, will send out the USBL probe. It works by an acoustic pulse is transmitted by the transceiver and detected by the transponder, which replies with its own acoustic pulse. Right. The USBL is used for science deployments to understand the positioning of the equipment, but it also can be used as a DP reference. Okay. I'm just going to touch a little bit on the propulsion equipment on board Nuyina. I'm not going to go into a lot of detail because this could be a whole presentation within itself. So the propulsion equipment on the Nuyina, as we explained before, has got 2 propulsion diesel engines at 9.6 megawatt each, the MAN diesels. There's 3 electrical DGs, which are 3 megawatt each. The Bergen's L9s. 1 2 megawatt Bergen, which is a 6-cylinder, which combines to give you a total power availability of 30.2 megawatt, which is quite a considerable amount of power. Not all of that can be used for propulsion. So with the power takeoff and power take-in modes, they provide 3.7 megawatt each, which gives an ability of a total propulsion availability of 26.6 megawatt. Okay, this is just a high-level arrangement drawing of the propulsion system. And the yellow is probably not that great, but in yellow is the propulsion engines. In red, you'll see there is the gearboxes, or the reduction gearboxes, which also includes the ice flywheels, which are only used in ice braking mode to provide additional momentum for ice braking. The light blue you'll see there is a combination of the electrical diesel engines, generators, sorry, and what we call the advanced electric drive electrical motors, the PTI, PTO. And then green, you'll see there is the clutches. What is not shown in this basic diagram is the shaft brakes, the shaft lock, and the thrust bearings. But this sort of gives you an overall picture of the total propulsion and electrical generation plant. Just to step through some of the key modes, there's a number of different propulsion modes that is available, which makes it quite complex. These are the key modes that it can do. Just explaining into that is that also you can't automatically go from one mode to another one. You need some modes you can go through and step to the others, some you cannot. So it's quite complex from a control point of view for propulsion. But so there's a silent mode, and that's used for acoustic data collection. That's on the electrical drives. That's up to 8 knots, and that turns off certain pieces of equipment to make it low noise. There's transit AED, that's for up to 12 knots of C state 5, that's only electrical propulsion. Transit PDE, that is for max transit of 16 knots. Transit PDO is the same. The only difference is the electric drives are used as generators and they provide power back up to the electrical side. There's combined mode, which is really ice braking, where it's a combination of both the electrical drives in PTI mode, which is power take-in, and also in propulsion, in mechanical propulsion. And then there's DP mode, which uses both electrical and mechanical. The electrical drives the 4 thrusters, the mechanical drives the CPPs and the other 2 thrusters. So from an electrical point of view, this is a bit of a high-level diagram of how it goes together. I'll just sort of step through the modes. So Hopefully you can see that. That's the silent mode. So at 8 knots, we talked about, power comes from the DGs, through the multi-drives, through to the advanced electric drive, through to the gearboxes on both sides. Transit AED mode, which you should see now, is not much different. It's exactly the same. It's just there's more equipment turned on and it's rated up to 12 knots. Transit PDE mode, as I explained before, is just propulsion diesels through the gearbox and into the clutches through to the props. Transit power takeoff mode is where the PDEs provide the power both to the electrical side and also to the propulsion side. So this is good in regards to maintenance to be done on the diesels, on the electrical. Just waiting for that to come through. Combined mode, icebreaking power take in. This is where it will take the electrical and the propulsion together to provide the 26.6 megawatt for icebreaking. DP mode, power takeoff, is slightly different. As I said before, the 4 electrical generators are supplying power to the 4 thrusters. The propulsion motors are providing power through to the other 2 thrusters through the AED and also the propulsion. And in this mode, the bus ties in the multi-drives are disconnected, which are there, which are a DC bus, and the switchboard is also not in parallel as well. The bus ties are open. Okay. That's the end of the propulsion. This slide we're stepping into now is the production and build photos. This is just showing a photo of, not a great photo, but a photo of the dock in Galati in Romania where Damen built the ship. They built the structure in the dry dock and then floated off into the wet dock. Just to give you a bit of context here, the block heights there are 0.9 meters. The water height, max water height is 10 meters. The minimum draft, the minimum clearance, is 0.3 meters, and the actual draft is 4.7 meters. At the time of launch between the dry dock and the wet dock, the ship was around 10,500 tons displacement. This picture here just shows one of the steps for floating it off, showing you all the mooring lines and the points. The next slide here is just going to a bit more detail of how it was floated off. We used inflatable buoyancy units, or IBUs, placed around the vessel with straps tied across the whole hull. Here's some pictures from construction. You see on the top left-hand side, there's some of the bags, IBUs I was talking about, and same in the middle photo with the straps going across all the way around. The top right-hand photo is it being floated off into the wet dock. And then the bottom photo is showing you with the superstructure consolidated on board. The next slides, I guess the left-hand side is the prop. Just to give you sort of some realisation of the size and weight of the prop. It's about 5 to 6 meters in diameter each, and they weigh 38 tons each. The hubs are around about 2 meters in diameter, and the fins are around 2 meters as well. The other pictures you can see here, the top middle is the bridge and mast superstructure being added. And you can see it in the right-hand photo in the wet dock, where it's being added, and then another photo of the hull consolidated. Okay. Just moving on from the production photos, moving into the test program. As Jonathan explained earlier, I was fortunate enough to go to SATS at the end of November last year for about 4 weeks. Also lucky enough to spend that Christmas and New Year's in quarantine in Australia. So on that trial of SATS, there was 9 Serco crew members and ourselves witnessing testing and trying to get a better understanding of the operations. So I'll just step through some of the modes. So the hats themselves, high acceptance tests, there was 196 of those. They were conducted mainly in Galati and finished in Vlissingen, and the vessel was towed over to Vlissingen. The types of tests that are conducted were just about every type of test for every single system. The SATs, which I said before, were in November last year for about 4 weeks. They were conducted between the Netherlands and Smith's Knoll in the United Kingdom. Most of the trials were done at Smith's Knoll. There was 49 tests. The types of tests that we conducted were really around proving the propulsion, the navigation, the speed, manoeuvring, FMEAs, and DP. This trials was mainly focused on class. So class was in attendance to witness all those class required tests, supported by contractors that Damen used as the suppliers, and of course the AAD and ourselves. After completion of the noise trials, of the SATs, the vessel went up to noise trials up in Norway, where I'll explain them in a bit more detail, but they did one test over about 4 days for the silent R notation. And then this year, at the start of this year, it went on to deep water trials out in the Bay of Biscay, in between France and the UK. There was 40 tests approximately there, and the main reason to do it over there is we needed really deep water to be able to do some of the science tests, the science equipment that's needed to be able to operate up to the depth of 25,000 meters. The next set of trials, which is forecast soon, is up Bergen, Norway, and it's actually breaking ice, testing cold climate conditions and operations. So just some photos from the SATs at Smith Knoll. The top left hand is the roughest day we saw. The top right hand side is one of the Bergen diesel generators. You'll see the dining room on the left hand side, and just a picture of where we're testing at Smith's Knolls location. Just some more pictures of Muyina. Looking forward, top left-hand corner, hangar deck, helo deck on the right-hand side. Bottom left, you've got some of the science trawl equipment, and bottom right, you've got the A-frame. Stepping into the noise program, as we said before, it was done in Norway. It was mainly really to prove the noise that was generated from the vessel, underwater noise levels, and for the silent R notation. We used 2 transducers with the science tender and did multiple passes past those transducers. at different speeds. We also measured some of the noise of the different equipment inside the vessel at the same time for the propulsion motors and the diesel generators. This location was picked due to the fact there was low interference of background noises and reverberation due to reflections of the walls and the sea bottom. That's a typical noise proving ground for most of the ships in Europe. Just stepping into some of the photos that we took from the noise trials. You can see a really good one in the centre of the A-frame and the helicopter deck looking aft. As explained before, in the test program for deep water trials, they experienced a bit more rougher conditions. So the bottom left picture is again the science winches. The middle bottom picture is showing the CTD being launched, and the A-frame being used as the right-hand picture. As stated before, we needed around 2,500 metres for the science sensors to use them and for fishing and CTD. Okay, just stepping on from sea trials. The next part of the journey is to voyage after acceptance for the vessel to come down to Australia and to Hobart. It's expected to take about 6 weeks at about 10 to 12 knots coming down. At the moment, as you can see, there's a couple of proposed embarkations, mainly people leaving then arriving due to the magical COVID, but just really fuel, resupply, continue on. When it arrives in Hobart, it will need to go past customs clearance and inspections, and from there we'll have a few weeks to prepare for its first voyage down south. Okay, just going over a summary of what I've shown today in the presentation today. Nuyina provides an increased capacity and capability over the existing Aurora, provides a significant increase in the marine science capability, requires a number of different propulsion modes for the different multiple operations it needs to do, can break ice up to 1.65 metres at 3 knots. By the time it's completed, we would have conducted 300 tests. On completion of ice trials and the delivery voyage, it will arrive in Hobart, and we should expect it at the end of the year or sometime this year. This picture here is just a render of comparison of the sizes between the Aurora and the Nuyina down in Hobart at Mach 3 and 4. When it comes alongside, it actually will be housed at Mach 6, which is a little bit more to the right. Okay, that ends the presentation.